Good morning to everybody again. Well, as a matter of fact, Massimo Ripa yesterday gave some information on my institute since he's a co-worker in my team. My institute, anyway, is located in south of Italy. It's located in Pozzuoli. And my unit focalizes on the study, realization, and optical characterization techniques of nanostructured composite materials, of metamaterials, photonic crystals, photonic quasicrystals, for application in photonics, optoelectronics, and biosensing. And all these activities are performed in 4 different labs in my institute, which are under our control. And these labs are the Nanocomposites and Soft Metal Lab, the Smart Materials Lab, which has been founded and started thanks to the PulseCom project, our European project. Then we have a Nano-fabrication Lab, which is the Electron beam lithography lab, and a Characterization Lab, which is the integrated optic lab. So our activity focalizes on nanotechnology and materials in order to make composites devices. What we do in our labs is to start from simulation and design. Then we go through fabrication of our structures, and finally we characterize them. You see here just some pictures of a photonic crystal realized in our lab. So what we do is to make plasmonic and polymeric nanostructured materials. In the last years, we focalized mostly on 2 specific applications. One is the food safety and, of course, biological applications. And Massimo also showed yesterday the combination of LSPR and SERS technique. But I will go in details on what we do with these techniques. And the other part of our activities, main part of our activities, is the applications in liquid crystals and isopolymers. And for example, also the realization of devices which are based on photonic liquid crystals and for electro and all optical control. And this part of the activity, of course, is part of the PulseCom project here. So the outline of my talk, I will start with a description of cutting-edge materials. I will go through the top-down technology that we employ for fabricate these materials. And I will just show you some of the applications with which we try to work. So let's start with cutting-edge materials. So I spoke of metamaterials. When we speak of metamaterials, we have to deal with characteristic parameters. So you see here A, which is a lattice parameter. And you see also in the picture on the right here, okay, A is a distance between single elements nanostructured on a substrate. And you have to deal with a wavelength of light which is interacting with these metamaterials. So if you have a look to this scale on the top of the slide, you will see that according to the dimension that we have, if we have, for example, a lattice parameter in our structure, which is less than the wavelength of light with which it is interacting, you have that the material somehow is described, the properties are described using Maxwell equations usually. When you have a structure where the lattice parameters is comparable with the wavelength of incident light, you have in this case that the structure dominates, and this means that usually the properties of this interaction of these materials are mostly determined by law of diffractions. And the case when you have that the lattice parameters are much bigger than the wavelength of incident light, in this case properties of materials are described by the use of geometrical optics. So what is a metamaterial? Metamaterial is, let's say, an engineered composite where in which you have properties which are usually not observed in nature and which are usually not observed in the constituent materials. So you have that the superior properties of a metamaterial somehow results from the specific engineered constructs. So in a metamaterial, you expect to have one or more properties which are, let's say, pretty extraordinary compared to the properties of the ordinary constituents of the metamaterial itself. So somehow we can say that the whole is much more than the sum of its parts. Well, in metamaterials, I think that almost all of you saw Harry Potter's in the movie, famous movie. As a matter of fact, in Harry Potter, you have the invisibility dress of Harry. And as a matter of fact, this is not, well, it's not a joke. Somehow this picture, of course, is not a true picture, but the concept is a true concept. The cloaking effect, that is the invisibility, can be realized with metamaterials. Now, this picture is very nice because it has been taken some years ago in Hong Kong. And in this picture, you have, well, the main people, the main founding fathers of metamaterials, still, all of them still alive. And you have Nader Engheta, David Smith, Yuri Kisher, Ortho Ines, Roberto Merlin, Eli Jablonovich, and John Pendry, who were attending at the same time the same conference. It was really a great experience to attend their lessons all together. It was a unique chance to have this possibility. Here you have some examples of metamaterials which have been fabricated in our labs. And you see here that the dimension in each case of each structure are pretty small. Let's say starting from 100 nanometer to 170 nanometers. So very, very small structures. In the frame of metamaterials, you have, for example, photonic crystals. Photonic crystals are characterized, you see on the right side, an example of a structure that we usually fabricate in our labs, are characterized by having lattice constants which are comparable to the light wavelength, the incident light wavelengths. These materials, as I said before, in this case, their properties are governed by diffraction of the periodicity of the structure. You have different examples of photonic crystals in nature, like you see diffraction effects in the wings of butterflies, which are naturally photonic crystals. You see different pictures of different butterflies. And here you have three examples of 1D, 2D, and 3D photonic crystals, where 1D means that you have periodicity in one direction, 2D in two dimensions, and 3D periodic patterning is in three directions. Another category of very interesting photonic materials are photonic quasicrystals. Now, photonic quasicrystals are characterized by being materials with a quasi-periodic dielectric function. They exhibit very fascinating optical properties, and their properties are in the middle between the properties of disordered materials and of those of periodic structures. As a matter of fact, there was first evidence of a photonic quasicrystal structure. You see in this tomb tower in Iran, and well, you can see a sort of aperiodic tracery, which is a quasicrystal. Then in 1974, Penrose studied a specific set of tiles used to cover a surface, and these also are quasi-crystal structures, until in 1984, Shechtman from Technion University officially discovered the quasi-crystal structure. Also in nature, you can see some examples of photonic quasi-crystals, like in algae, as reported in these figures, or in sunflower. This is a quasi-crystal structure, or again in wings of some insects. You see on the right side same image focalizing on this insect, and as you can see, this exhibit a quasi-periodic structure naturally in the insect. So you saw this characterization also from Massimo's slides yesterday. Photonic quasi-crystals can be characterized with this technique. This is the setup that we have in our lab. When we do want to see the quality of our quasi-crystals, we perform this kind of characterization. And what is very interesting is that, of course, in case of octagonal, for example, the first one is an octagonal structure, you have that diffraction has 8 points of diffraction due to the specific order of this quasi-crystal. Then you have an example of dodecagonal quasi-crystal where you have 12 points of diffraction when light is crossing through these materials. And this is another kind which is named two-Morse structure. This has been shown by Massimo as well. All these structures have been designed and realized in our labs. Well, we have both periodic, quasi-periodic structures, so periodic crystals like these ones, or the possibility to make periodic quasi-crystal structures. And again, when you when you have light crossing through these materials, again, you have very fascinating diffraction effects. In this case, you have a laser light, a green laser light crossing, going through these materials. And this is also more fascinating when you have white laser light going through these materials. Well, let's go to the technology, top-down technology that we use in order to make these structures. Well, the kind of technology that we have in our institution is electron beam lithography. It's a very nice technique which gives you the possibility to make very fine patterns. You see in the cartoon how it works. That is, you have a scanning of beam of electrons across a surface which is covered with a resist film. This film is sensitive to these electrons, and in this way you have a deposition of energy in the kind of pattern that you want to realize. Well, let's say that the most important aspect, the most important issue of this technique is that it has a very, very high resolution, and this means a few nanometers. Well, just a sketch to see how we do make our structures. From the beginning, we start from a substrate, glass substrate. On the glass substrate, we have a spin coating of a resist film, and usually we use a resist which is commercially known as ZEP material. Then second part is to, of course, the nano patterning using the electron beam lithography technique. After it, you have a chemical development, and so what you get are holes in the ZEP material, in the resist material, and these holes, of course, have been designed according to specific designs that you want to realize. Then the other step is the pattern transfer by metal deposition. So what you do is that you, by thermal evaporation or by E-beam process, you transfer a metal on the top of your structure. Then at this stage, you can stop here. And if you stop here, what you do have is, let's say, holes in a metal structure according to the design that you want. Or you go through another step, which is a lift-off step, through which you have the final plasmonic nanostructure, which is this one, where you have only, let's say, metal nano rods, nano structures, with which is not holes but are pillars in this case. So already Massimo already show you the kind of characterization that we do. We have a homemade LSPR setup, and he showed yesterday as it works, the characterization. Then we have also possibility to apply CERS technique, which is amplified Raman spectroscopy, and you see in the pictures three different setups that we have at different wavelengths that we can perform. Exciting wavelengths like 785 or 1064 nanometers. So just go to applications. There are different applications that you can have using these materials. We focalized on optical nanobiosensing, but you can have also like control. Well, nanobiosensing is based on the realization of nanobiosensor made of two different parts, which is, let's say, a biorecognition layer where you capture the analytes, and transducer, which is used to provide the signal that you want to analyze. Transducer can be different properties of materials like electrical, optical, magnetic, mass thermodynamical. In our case, we do use optical sensing. So we realize sensors based on refractive index detection, radiation, or CERS sensors. And the kind of biorecognition layer that we use are phages or antibodies, while our transducer are the plasmonic nanostructures that we make. So Massimo already showed you that what is very important in plasmonic nanostructure sensors are the realization of plasmonic resonances, which affect the performances of the sensors. So like sensitivity, limit of detection, and reproducibility. But at the same time, you have that the size, shape, and symmetries of your structures affect plasmonic resonances. So you can tailor the properties that you want according to the kind of design that you make of your structures. Well, I just give you an information. Okay, when can I say that I realize a good biosensor? Okay, the requirements that I do need are highly sensitivity, uniformity, and reproducibility of the material, of the structures. But these properties are given by novel nanomaterials and nano-fabrication, while specificity and selectivity are provided by how good is the functionalization that we perform. So at the end, we have that in order to develop new diagnostic tests, the main important issues are rapidity, sensitivity, and specificity. Just very, very quick definition. We use optical nanobiosensing in terms of localized surface plasmon resonance biosensing. And how does it work? You have it when analyzed attached on your nanostructure, you have that resonances shifts, and the shift depends on the concentration of the analytes on the structure. So in this technique, you have that your plasmonic nanoparticles are the transducer, and this is what converts changes in the local refractive index, and this is converted in spectral shifts in the localized surface plasmon resonance band. So this technique provides high sensitivity, and you can couple this with CERS, with Raman spectroscopy, which provides specificity. What we use is enhanced Raman spectroscopy, and we have enhanced Raman spectroscopy coupling the high molecular specificity of Raman spectroscopy with the high sensitivity provided by the plasmonic nanostructures. Well, Raman cells biosensing is like a molecular fingerprinting. Also, Massimo before showed some spectra due to Raman techniques and due to CERS technique. It's a unique, you can have unique vibrational spectra, which gives you the possibility to distinguish molecules. Okay. These are other examples of nanopatterns that you can realize with different interesting, let's say, light control properties. So I just conclude showing a list of people which are involved in my team, involved in these activities, which are Massimo Rippa, Valentina Marchesano, Ambra Vestri, Domenico Sagnelli, and Amalia Dadino, and also different people with whom we collaborate very strongly in the projects in which we are involved. And Wroclaw University of Science and Technology with Kaja is one of these institutions, but we really collaborate a lot with the Photonics Institute of Ningbo in China, with the Zooprophylactic Institute of South Italy, and with the Istituto Superiore di Sanità in Rome. And now, thank you for your attention.